Okay, good morning. Let's get started. Okay. So, we have been learning about MRAM, magnetic random access memory. Okay, first we learnt about writing mechanisms. How do we write information in MRAM? So, writing is basically switching the magnetization of the free layer to be either parallel to the reference layer or anti-parallel to the reference layer. So, this to achieve this one I explained three different methods. First method is to send a current through a wire which will produce a magnetic field. Okay, not one wire, two wires. So, we produce two magnetic fields, one along the easy direction, another along the hard direction, and we use this magnetic field to switch the magnetization of the free layer. Okay, that is one thing that we studied. Second method we studied is spin transfer torque mechanism. Okay, so, in this case we send a current through the magnetic tunnel junction device. The reference layer polarizes the electrons. Okay, so, one type of electron predominantly goes to the other side, and that transfers angular momentum to the magnetization. Then finally, we have the switching. So, that is the spin transfer torque mechanism. Then the third concept I introduced is spin orbit torque. So, in the case of spin orbit torque, we have a heavy metal layer. So, this spin orbit coupling in heavy metal layers larger. So, when you send a stream of electrons, one type of electron go to the top surface, another type of electron go to the bottom surface. So, if you have a ferromagnetic layer on top of a heavy metal, we can use these spins get accumulated here. So, we can use these spins to switch magnetization. So, based on this method we can have SOT MRAM. We learned that SOT MRAM is a 3-terminal device. It is faster, and in this MRAM device we are not sending current through the magnesium oxide layer for writing information. So, it is also more it has more endurance, which means you can write many times and still the memory device does not get spoiled. Okay. So, these are the three concepts that we learned day before. So, yesterday we were learning about the important aspects related to storing of information. So, MRAM is a non-volatile memory, which means it is supposed to keep the data even when you switch off the power. So, the storage aspect is important. Okay, so, when it comes to storing aspect, we know that materials have anisotropy, and this anisotropy creates an energy barrier. So, this energy barrier will prevent the magnetization from being flipped from one direction to the other direction. Okay, so, this energy barrier is the one that helps to retain the information, and this energy barrier is the one that makes the MRAM non-volatile memory. So, NVM is non-volatile memory. Okay, so, typically this energy barrier is designed to be more than 40 kBT or around 60 times the thermal energy kBT. So, if the energy barrier is much larger than thermal energy, then the data will be stable for 10 years. Okay. So, we learnt about two types of MRAM. One is called in plane MRAM. Okay. The second type is called perpendicular MRAM. So, as the names imply, in plane MRAM, the magnetization of the free layer and the reference layer are all parallel to the wafer plane, and in the case of perpendicular MRAM, the magnetizations are perpendicular to the wafer plane. Any question? No. So, in the case of in plane MRAM, when we use say the magnetic field assisted switching, the MRAM is somewhere here. We do not want to use a elliptical MRAM. Okay. Elliptical MRAM occupy more area. Okay, so, because of this it is not desired, we use a circular MRAM. Okay, so, in circular MRAM, we want to define some easy direction. So, to do that we use antiferromagnetic layer at the bottom of ferromagnetic layer. So, if you have a MTJ where this is the reference layer, then this is the magnesium oxide layer, then this is the free layer. In order to pin the magnetization of the reference layer in one particular direction, we use an antiferromagnetic material. Okay. Then we follow the recipe that we learnt and induce an exchange bias. Okay, so, this is the simplest configuration of in plane MRAM. Okay. But in this case, the reference layer can generate some stray magnetic field which can influence the magnetization direction of free layer. So, we want to reduce or eliminate the stray field from the reference layer. Okay, so, for that purpose, instead of having one reference layer, we split this into a synthetic antiferromagnetic structure where by inserting a thin layer of iridium we can achieve a configuration like this. Okay. So, instead of one ferromagnetic layer, now let us say we have two ferromagnetic layers separated by ruthenium, we have anti-parallel coupling. So, in this configuration the stray field will be contained within the reference layer. Okay. So, the stray field from here will go here and the stray field from the top of the reference layer will go to the bottom of the reference layer. Okay. So, if you have magnesium oxide and a free layer here, the free layer will not see any stray magnetic field from the reference layer. Okay. So, these are the advanced designs of in plane MRAM. Okay. Then we learnt that there are two problems, at least two problems with respect to in plane MRAM. First problem is thermal stability. So, we have learnt that the KUV has to be greater than 60 times kBT. Okay, so, in the case of in plane MRAM, we are using materials like cobalt iron boron with a low Ku. Okay, so, as a result, the KUV is not high. So, since Ku is not high, the volume has to be larger to compensate for this kBT. So, the smallest volume will indicate that the diameter of the smallest device can only be around 60 nanometer. That means, if you make an MRAM smaller than 60 nanometer in diameter, it will start fluctuating, magnetization will start fluctuating. So, this is the limit. So, we can go down from say 120 nanometer all the way to 60 nanometer, but we cannot go below this. If you go below 60 nanometer, you will lose the data, you cannot store the information for 10 years. So, that is one problem that we learnt. The second problem we learned is that, let us say magnetization is pointing in this direction, you want to switch the magnetization to point in the other direction. Magnetization being an angular momentum, it does not just flip, okay, it goes through a precession, okay, it precesses, then finally goes to the other state. Okay, so, during the precession, the magnetization is here, here and so on. Okay. Magnetization spends long time in the perpendicular direction. Okay. So, instead of going from here to here this way, it goes like this. Okay. It spends much longer time in the out of plane direction, and we learnt that if you have a magnetization in the plane and if you want to apply a certain magnetic field and bring this magnetization to be parallel to H, that field is 4 pi m s. Okay, so, this field is much larger than the anisotropy field. Okay. 4 pi m s is much larger than, say 100 times larger than H k, something like that. The field that retains the information, the anisotropy field that retains the information in plane MRAM is 100 times smaller than the 4 pi m s. Okay. So, we are spending too much energy to write. Okay. The energy to write is much more than the energy to store information. Okay. So, it is a waste of energy. Okay. So, because of these two problems, researchers started working on perpendicular MRAM. So, in perpendicular MRAM, if you have magnetization in the perpendicular direction and if you want to bring it to in plane direction, you need to apply a field H k. Okay. So, this is the same field that is used for storing information also. So, that means, if you bring the magnetization from pointing up to pointing down, even if the precession happens, the energy spent to write is not more than the energy to store. Okay. So, the energy for writing is same as the energy for storing. Okay, so no extra energy spent like in the in plane MRAM. So, that is one point. And the second point is that we can use high anisotropy material. So, because of high anisotropy material, you can achieve high thermal stability. High thermal stability, and because of that, you can potentially make MRAMs smaller than 60 nanometer. Okay, so, because of these two reasons, people started looking at various perpendicular MRAM materials. So, I told you that people looked at materials like terbium, iron, cobalt, platinum, multilayers, iron, platinum, etc. Okay, but they all have some problem, either their damping constant alpha was high, which means they consume more energy for switching magnetization, or they have corrosion problem, or they have problem in achieving high TMR and so on. Okay. So, for a long time people did not know how to achieve perpendicular MRAM until 2010, when the group of Tohoku University, they came up with this structure: tantalum, cobalt iron, boron, magnesium oxide, where if you make the cobalt iron boron very thin, for example, around 1 nanometer, you can achieve perpendicular MRAM. Okay. So, this was an exciting result. Okay. So, this discovery enabled the perpendicular MRAM. Okay. So, this material has no problem in achieving high TMR. Okay. This material is not corroding, okay. Corrosion problem does not exist, and this material also had a reasonably low damping constant. So, all the things that we wanted from a material for perpendicular MRAM was possible because of this particular discovery. Okay. So, this was the first discovery that enabled MRAM from going from 60 nanometer down to around 35 nanometer. Okay, so, after this people started improving the tantalum, cobalt and boron, magnesium oxide. Okay, so, instead of one tantalum, cobalt and boron, magnesium oxide interface, people came up with concepts like having tantalum in the middle, having two magnesium oxide like this. So, now you see there are two interfaces of tantalum, cobalt and boron, magnesium oxide. Okay. So, when you stack them like that, then you have two interfaces. So, basically you are adding, the volume gets doubled. So, because of this reason, this particular configuration could go to around 25 nanometer diameter. Okay, so, after this people also have started exploiting shape anisotropy. By making MRAMs tall and small, they get MRAM MTJs like this. Okay. So, here because of the shape anisotropy, the magnetization will point in the perpendicular direction. So, this is called a nano MTJ. So, with this researchers have shown even like 5 nanometer MRAM. Okay. I mean theoretically and maybe lab wise experiment this one works, okay. But we do not know how the industry will be able to make this tall MTJ. Okay. So, if you want to make tall MTJs in the industrial application, maybe there will be many challenges. Okay. How do we etch them? There are some challenges like that, but theoretically it is possible to make 5 nanometer MRAM by using this concept, nano MTJ concept. Okay, so this is what we learned yesterday. Any questions there? Okay, if not, let us move on to today's topic. Today we are going to talk about how do we read information. Okay, most of the concepts related to reading we have already learnt. So, today I will just briefly go through, will not spend much time here, and the theory also I am not very confident. So, I will just briefly show you a lead, then all of you can read the papers to understand the theory better. Okay. I will highlight the technical aspect, how, what are the challenges when we try to implement in the industry and so on. Okay, so we have been learning about how do we write information, how do we store information. When it comes to reading the information from MRAM, the magnetoresistance is the one that determines how do we read information. Okay. So, we have already seen this many times. So, we are okay. Let us skip this one. So, we learned that there are 3 types of magnetoresistance: AMR, GMR and TMR. AMR is typically 2%, and I told you TMR in the industry can be around 200%. And if you look at GMR, for most practical purposes, GMR is only around 10%. Okay, so, when you send a current through a GMR device, let us say you have a free layer, copper, some reference layer, you send a current to read the 2 resistance states of GMR device. Let us suppose the parallel configuration gives rise to 100 ohms, okay, and the anti-parallel configuration gives rise to 110 ohms. Okay, so, this is the 10%, right. So, 10% GMR means the 2 resistance will be different by about 10%. Okay. So, anti-parallel, let us say it gives 110 ohms, parallel gives 100 ohms, and you send a current of 100 microampere to convert this current into voltage, then you will get like 10 millivolt and 11 millivolt. Okay. So, this is the difference between say bit 0 and bit 1. Okay, this 1 millivolt difference is too difficult to read. Okay. So, because of this reason people do not use GMR, they go for TMR, which gives rise to 200% tunneling magnetoresistance. So, as we learned before, tunneling magnetoresistance has a long history. Even though it was observed in 1970s at around 4 Kelvin, in 1990s people observed TMR at room temperature. Okay. This scientist from MIT and the scientist from Tohoku University came up with the TMR observation. So, at this point of time the tunneling magnetoresistance was only around 12-13% kind of thing, okay. But it was exciting for the hard disk industry, because hard disk industry was already working on GMR and there was hope to increase the TMR to even better values, so that we can read the information in a better way. So, again hard disk industry is the one that made the TMR progress first. Okay, so, if you look at the progress of the tunneling magnetoresistance as a function of year. So, you will see two regions. Okay. So, in one region the tunneling magnetoresistance grows like steadily, then there is a region where the tunneling magnetoresistance has a huge jump. Okay. So, these are because of two types of physics and two types of material. Okay. So, in this region 1994 to 2004, people were looking at amorphous material as the barrier layer, tunnel barrier layer. Then somewhere in 2004, people started using crystalline material, crystalline barrier. Okay. So, here it is aluminum oxide. Here when it comes to this point, it is magnesium oxide barrier. Okay. So, this discovery, a theoretical proposal of magnesium oxide led to a larger TMR in the later part. Okay. Okay, again this is the definition of TMR. So, let us say you have certain resistance in the antiparallel state, certain resistance in the parallel state. So, the difference divided by the resistance of the parallel state gives rise to TMR. Let us say TMR is 200%. Okay, so, this is currently widely used in the industry. Okay, so, if the parallel state gives rise to 100 ohms, okay, then antiparallel state will be around 3000 ohm. Okay, that gives rise to 200% change. Okay, now you send the same current which I showed you before. Now you have a free layer, magnesium oxide, reference layer. So, you send a current of 100 milliampere. Okay. So, if you calculate the voltages and the difference, now the voltage difference will be around 0.2 volt. Okay. So, this 0.2 volt is enough to sense 0 and 1. So, if you remember the GMR example, the difference was only like 1 millivolt. Okay. Now, it is like 200 millivolt. Okay. So, you can 1 millivolt or 10 millivolt, but now you have 200 millivolt, which is enough to sense 1 and 0. Okay. So, because of this reason, people do not use AMR or GMR, people use magnesium oxide as the barrier, which can give rise to 200% TMR for reading information in MRAM. Okay, so, here the difference is only 1 millivolt, which is not enough. So, we need a signal swing of 0.2 volt. Okay. Signal swing means low resistance state gives certain voltage, high resistance gives you certain voltage. So, this difference in the voltage has to be at least 0.2 volt. Okay, that is possible with this magnesium oxide. Okay, so, if you look at the history, so for many years until 2003, people were working on amorphous aluminum oxide, improving the property of aluminum oxide by various processings. So, they could go all the way to maybe 60% TMR. So, the first paper reported around 12 or 13% TMR. So, from here all the way they could go to 60%, slowly improving the processes, but they could not go beyond. Then a breakthrough came in 2004, where a group from Japan came up with 84% TMR. Then Stuart Parkin, he came up with 220% TMR. Then the same group in Japan, they came up with 230% TMR and so on. Okay. So, the 2004 is the onset, where the magnesium oxide made a breakthrough. Okay, so after that people did some research. So, in the laboratory we can have 600 to 1000% TMR, but as I mentioned, in the industry they can achieve 200% TMR reasonably well. Okay. Okay, so, I told you that there are two regions of TMR. So, in one region people used So, I told you in one region people used aluminum oxide, in another region people used magnesium oxide. Okay, so, the theory behind aluminum oxide kind of a tunnel barrier can be explained using Julian model. So, we briefly saw this during our TMR sensor theory part. Okay. So, in the case of magnetic tunnel junction, we have two ferromagnetic layers. So, their magnetization can be parallel or anti-parallel, and we have a tunnel barrier. Okay. So, in this case we just ignore the the tunnel barrier. So, it can be aluminum oxide or anything. So, Julian model is independent of the tunnel barrier. So, the TMR value that we get in Julian model depends only on the ferromagnetic layers 1 and 2. Okay. So, let us say this is ferromagnetic layer 1, this is ferromagnetic layer 2. In Julian model, the TMR depends only on these two ferromagnetic layers, it does not discuss about the tunnel barrier. So, that is a drawback of this model. Okay. So, in this case the density of states on the left side ferromagnet and the right side ferromagnet. Okay. So, the majority electrons in the left side and right side ferromagnets, and the minority electrons in the left side and the right side ferromagnet. For this parallel configuration is the first term. Okay. So, Gp is these two terms. Okay, then there is a tunneling of electron when the two magnetization are anti-parallel. So, that is given by these two terms. So, the density of states in the left side and the density of states of, we are talking about. So, when we say this, this is N L up, this is N L down, okay. Then here okay, so this is the terminology. Okay, so the electrons going from this side to this side, or this side to the other side, this to this, this to that. So, we include all the terms there. So, that gives rise to the TMR. So, finally, if you look at this model, it will only talk about the polarization of the left electrode. For example, let us say this is ferromagnetic one. So, the polarization of the ferromagnetic layer 1 and the polarization of the ferromagnetic layer 2, only they determine the tunneling magnetoresistance. The barrier does not come into picture. Okay, so, the definition of polarization is given here. So, let us say we talk about only one ferromagnetic layer, let us erase this one. Okay, so, polarization is basically the density of states of the majority electrons minus the density of states of the minority electrons divided by the total, that is basically the density of states. So, TMR will be only decided by the ferromagnetic layer. Okay. So, this model will not work all the time. For example, if you are studying aluminum oxide, so aluminum oxide or some hafnium oxide or some oxide as your variable. Let us say you have two ferromagnetic layers, identical ferromagnetic layer, but if you are inserting various oxides, for example, aluminum oxide, hafnium oxide, some titanium oxide whatsoever, right. You are studying the different oxides and measuring the TMR, then you cannot use Julian model to explain your result, okay, because Julian model ignores the barrier layer. So, it only considers the probability for electrons to tunnel from one side to the other side based on the ferromagnetic density of states. Okay. So, this model explains TMR only based on the ferromagnetic layer properties, it ignores the barrier layer property. Okay. So, if you look at some results like this, so here it is talking about polarization of the left side electrode, right side electrode and so on. So, if you make both the ferromagnetic layers to have a large polarization, you will have large TMR. Okay. So, that is basically the model. So, it does not talk about the role of a barrier layer in TMR. Okay. So, if you are studying the barrier layer effect on TMR, you cannot use this model. Okay. Then somewhere around 2000, this Professor Butler came up with another model based on first principle calculations, not just model. Okay. He proposed that if you are, instead of using aluminum oxide, if you make magnetic tunnel junction based on something like this iron, magnesium oxide iron in a particular crystal structure like 001, you can achieve very large TMR. I think according to this model, the TMR can be like 10,000% or even larger, something like that. Okay. So, this is one example where theory comes first, experiment comes later. So, you all know that the theory for laser was given by Einstein. Okay. So, Einstein came up with the theory of laser somewhere in 1920s, but it took around 30-40 years to experimentally realize laser. So, in a similar sense, this is a very useful theory which predicted that you can make magnetic tunnel junction with high TMR if you follow what this model suggests. Okay. So, in this case, this is Professor Butler. He carried out first principle simulations. I do not know, some of you may be doing density functional theory, those kind of things. So, he uses those kind of theory, and he say that electrons in certain band, particularly this delta 1 band, can tunnel through the magnesium oxide barrier more easily than the electrons in the other band. So, if you consider the tunneling for parallel case and anti-parallel case, there will be a huge difference. Okay. So, which can lead to a high tunneling magnetoresistance. Okay. So, this is what he predicted. There is a very nice paper. So, if you are very interested in the theory, you can go through the paper. I can pass to you later. Okay, so, in this paper he is using magnesium oxide with the crystal structure. So, if you consider the aluminum oxide is amorphous, whereas the material Professor Butler studied in his paper is magnesium oxide, which is crystalline. Okay. So, magnesium oxide has certain crystal structure. So, these blue atoms are magnesium, and the red atoms are oxygen. Okay. So, they are arranged in certain way, and there are several crystal directions. So, when we learnt about crystal, I told you that depending on which way you look at, you can have various crystal planes, crystal direction, and so on. Okay. So, here again, depending on how you look at, you can have like 111 or 001, 110 and things like that. Okay. So, in this case, for example, these are the delta band directions, and these are the directions where the probability for electrons to tunnel from one ion layer to the other side of the magnesium, another ion layer. The probability for electron to tunnel from this side to the other side when the two magnetization are parallel is higher through this delta band. Okay. So, that is what he proposed. Okay. So, they look at various symmetries. Let me jump through many slides. Okay, now let us come here. So, here we are talking about layer number. For example, this side represents ion layer, one side of the magnetic tunnel junction, and from here onwards it is again ion, the other side of the magnetic tunnel junction, and this region represents the magnesium oxide layer. And this picture shows the density of states for parallel configuration. Okay, so, if the difference in the density of states is not much, okay, then we can say that the band matches and the probability for electron to tunnel from this side to the other side is higher. Okay. So, if say for example, this band does not match, okay, here there is a large mismatch and so on. So, this means tunneling probability is less, and here may be almost impossible. Okay. So, he calculates the density of states for various configuration. So, here is like the majority electron, this is for minority electrons to go through the parallel state. So, all these things he looks at, and he says that for this particular delta 1 band, the band matching is very good. So, the electron tunneling probability is very high. Okay, so, if you look at the anti-parallel configuration, the spin up electron can go reasonably okay, but the spin down electron cannot go. Okay. Okay, so, based on all these calculations, okay, let me skip this one.
Sir, what's K parallel equal to 0?
What is 0?
K parallel, the third one.
K parallel is equal to 0. Actually, I do not remember this one, that is why I skipped this slide. So, the most important point is when you have this kind of crystal structure, the probability for electrons to tunnel, especially through the delta 1 band, is higher, and we will have the low resistance state. And when you have anti-parallel, the probability for electrons to tunnel is less. So, we will have high resistance. And the key difference between the aluminum oxide and magnesium oxide is that this low resistance of the magnesium oxide is actually much lower than aluminum oxide. Okay. Let us say in magnesium oxide you have like 3000 ohms versus 1000 ohms. In the case of aluminum oxide, you will go from 3000 ohms to probably like 2200 ohms, something like this. Okay. So, for parallel state, you will have much lower resistance in magnesium oxide. So, that is the key result, and that is observed only when you have grown magnesium oxide in BCC 001 texture. Okay. So, this crystalline texture is important. So, all the calculations that I showed you before are based on the magnesium oxide in the 001 texture. Okay. Okay. So, now I will show you some experimental results to show that the magnesium oxide 001 is important. Okay. So, in this table you will see various compositions of the reference layer and various compositions of the free layer and the TMR of the structures. Okay. So, normally when you have cobalt, only cobalt can exist in HCP or FCC kind of structure, and iron is BCC. Okay, let us say you have an alloy which is 100% cobalt and 100% iron. So, you vary the cobalt and the iron when you go from left to right. For example, let us say this is a cobalt 50, iron 50, something like this. Okay, so, depending on the relative composition, there will be some region where when the iron is lower, let us say cobalt is 85, iron is only 15. Until this region, this will be FCC, and beyond this region we will have BCC. Okay. So, depending on the ratio of cobalt and iron, you may end up having BCC structure or FCC structure. Okay, so, if you look at this table, here iron is less, 10% only. Okay, so, 10% iron is here. So, this is FCC, and in this case again cobalt iron is 10, iron is 10. I do not know, can you see from back? If you cannot see the letters, I can duplicate this slide. Okay, so this is BCC. Sorry, this is the FCC, this is the FCC, and so on. Okay. So, you will notice that when at least one of the layers is FCC, the TMR is very low, around 75, 50, something like that. On the other hand, when you have like cobalt 40, iron 40, both are BCC, then the TMR values are larger. Okay, so, this is what the theory predicted. I mean, the theory actually proposed. The theory proposed that you should use magnesium oxide with a BCC 001 texture between two layers of iron to get high TMR. Okay, people do not use only iron, they mix with cobalt to have certain other additional properties. So, because of that now we can get like very large TMR. Okay. So, in all these cases it's having BCC. Okay. So, when both sides have BCC structure, you will have high TMR. When at least one side has FCC, you will have low TMR. Okay, that is what is shown here. So, this is another demonstration of the effect of having magnesium oxide in 001 or say in some other phase. Okay. So, here magnesium oxide is in 001, which agrees with what Professor Butler proposed, okay. But this is not the one he proposed. Okay. So, here magnesium oxide is in 111 phase. So, if you compare the TMR, this sample gave rise to high TMR, this sample gave rise to low TMR. Okay. So, this is the reason I told you earlier that if you have cobalt platinum multilayers, let us say you grow cobalt platinum multilayers. So, typically this cobalt platinum multilayer grows in FCC 111 structure. Okay. So, this FCC 111 is not preferred, okay, because it will give rise to low TMR. So, if you remember a few days ago I showed you the whole stack of MRAM. So, there is a cobalt platinum at the bottom, there is a cobalt platinum at the top, and this was the synthetic antiferromagnetic structure. Then on top of this we have magnesium oxide and the free layer. Okay. So, at the interface I showed you that there is a cobalt iron boron. Okay. You can look at the slides later, but this is something I showed you before. I did not tell you the reason why we have this cobalt ion, because that time it was too early to discuss that. Okay, so the reason we have the cobalt ion here is to break the crystal structure following. Okay. So, if this cobalt platinum is FCC 111, okay. So, if this is FCC 111, if you grow this magnesium oxide directly on top of this, then magnesium oxide will grow in this 111 texture, then you will have low TMR. Okay. So, we do not want this one. So, to break that we insert an amorphous cobalt ion boron. So, now this is amorphous. So, on top of amorphous cobalt ion boron, magnesium oxide will grow with 001 texture. Okay. So, the TMR will not be affected because of this layer. So, when you grow materials, you have to think about what kind of crystal structures you are growing, whether this crystal structure will affect positively or negatively, you have to consider all these aspects. Okay, so, cobalt platinum multilayer is a good material for reference layer, because it has a large anisotropy constant. This will be stable even when you read or write information, but this has a problem of this FCC 111 texture, which can kill the tunneling magnetoresistance. So, to overcome this problem, people insert amorphous cobalt ion boron near the magnesium oxide interface. Okay, so, what people do is they deposit magnesium oxide on top of amorphous cobalt ion boron, and after every deposition is done, they will finally carry out some annealing at around 300 degrees Celsius for 1 hour. So, during that annealing, boron will go somewhere else, and this cobalt ion boron will crystallize into cobalt ion 001 phase. Okay. So, this is what this boron will go away, finally, you will have cobalt ion 001 phase. Okay. So, this is the procedure followed in the industry. So, for the industry production, there are two types of magnesium oxide deposition. One method is to have a magnesium oxide target, okay, and use radio frequency sputtering to get magnesium oxide layer. The second type is to use magnesium target. Magnesium is metal, okay, so you can use direct current sputtering. So, during the sputtering, they will deposit a thin layer of magnesium, then oxidize the magnesium to form magnesium oxide. Okay, so, this is the reason I told you yesterday that in the industry there will be many chambers. There will be one chamber to deposit metals, another chamber for magnesium oxide. They will use oxygen gas to oxidize magnesium to form magnesium oxide. So, they do not want this oxygen to contaminate all the other materials like ruthenium, cobalt and boron, all these things. Okay. So, usually oxide chamber is separate. Okay, so, as I mentioned, if you have materials with the FCC 11 texture, it is not good. So, we have to break this FCC 111 or BCC 111 texture, but we should focus on getting BCC 001 crystal structure. Okay, that is important. So, what are the challenges for industry? So, one challenge is the tunnel barrier quality. So, we are depositing 1 nanometer of magnesium over a wafer that has a diameter of 30 centimeter. Imagine you need to deposit 1 nanometer MgO. So, throughout this 30 centimeter, your magnesium oxide thickness has to be uniform. Okay. So, if it is just say even plus or minus 0.2 nanometer, okay, then the TMR of the device that you make here will be say 100%, and the TMR of the device that you make here may be like 250%. Okay, so there will be huge changes in the tunneling magnetoresistance. So, we need to ensure that this thickness is uniform throughout the 300 nanometer, sorry, 30 centimeter wafer. So, this is a challenge, but industry is managing. So, this is where the sputtering is superior. So, many of you guys may be using PLD or some other form of technique to deposit films, but they are not as good as sputtering. Okay. Sputtering is the one that is industry friendly, that can make practical devices. If you do MBE, for example, MBE may be very good in achieving a very good crystal structure, but MBE is not useful in the industry. So, sputtering is the best technique. Okay, let us do some question and go for tea. Okay, majority of you are right. Tunneling magnetoresistance. So, it's a T for tunneling. So, this should be the answer. I don't know why two of you are choosing this. Okay, next one. Okay, these 5 are not following what I am talking about. Okay. I said many times that in the Julian model the barrier is not considered, the TMR is decided only by the ferromagnetic layers at the two sides. It is a very simple question. Okay, next one. Okay, most of you are right, very good. Okay, next question is related to these three pictures. Which of these following MTJs will have the largest TMR? So, you have two ferromagnetic materials, they are in different crystal structures in like BCC, FCC. Okay, most of you are right, okay, because you have listened to what I am talking about. So, I repeatedly mentioned, not once, maybe 3 or 5 times I mentioned that we need BCC structured materials for high TMR. Any FCC will kill the TMR. So, B and C have FCC, so B and C are not the correct answer, A is the correct answer. So, when you go to conference, you cannot learn much, because the conference, the speaker does not repeat, okay? He just goes with the flow, he tells only one thing, only one time. So, if you listen attentively, you may learn what the speaker talks about, but when it comes to classroom teaching like this, I repeat things many times. So, we are not attentive all the time, right. So, sometimes we may lose focus, but I repeat 3 or 4 times. I also do a recap, so that at least one out of these 5 times you will listen and understand. Okay. Okay, next one. Here you type yes, type yes. Okay, if I do not see all correct answers here, I will have heart attack. Okay. You saved my life. Okay, that's all. We'll go for a break, then we'll come back and learn some domain wall memory concepts. So, regarding the question on quantum computing, I can say one thing where the spintronics could be useful. I mean, there could be many other areas, but I will just touch upon the memory. For example, if you use semiconductor based memory to store information, that won't work in quantum computing, where you are operating at temperatures below 4 Kelvin or around close to 4 Kelvin. Okay, so, that is going to be a problem. The normal memory won't work, but the spintronics memory can operate at any temperature, room temperature or 4 Kelvin, we can still achieve the memory. So, that is where all these memory technologies that you learn could be still useful even for quantum computing. Okay, with that, let us move on to the discussion on domain wall devices. So, you heard my talk yesterday, where I talked about domain wall devices for neuromorphic computing. Today, we are going to talk about domain wall devices for storage application. Okay. So, chronologically, this is the first concept. Neuromorphic computing was a newer concept, but we are talking in the reverse order. We talked about the latest technology yesterday, and we are talking about the earlier technology today. So, when I was like you, we used to store videos in these tapes. Okay. So, which the video will have a resolution of 333 times 480 pixel. Okay. Later, in 1990s, digital tapes with a better resolution came. So, these tapes used to store movies in this picture quality, which is like a DVD picture quality. Suppose you want to extract this whole video into a hard disk drive, the data will be around 12 gigabyte of data will be needed to store data. Okay. And early 2000s, we have this kind of camera where we could store videos in a hard disk drive. So, this camera had a 30 gigabyte hard disk drive, and we could store the video in those hard disk drives and so on. But now we have phones with 4K UHD cameras, and we store the video there. Okay. So, what all this means is that the video quality that we come up with keeps increasing, and as the video quality keeps increasing, the number of the data storage requirement keeps getting higher and higher. Now, most smartphones have 4K UHD, and some phones have 8K UHD. So, if you want to store uncompressed video, you need 86 terabyte per hour. Okay. And this is also another example where hard disk drive was used significantly. So, you would have known about the black hole image capturing. So, the black hole image capturing was made using telescopes throughout the world. So, all the telescopes collect data, and they were accumulated in 5 petabytes hard disk drive. So, this lady who is in charge of constructing the black hole image, so she displays all the hard disk drives. So, we have lots of hard disk drive which make 5 petabyte capacity. So, we store all the information there. Finally, we came up with one image representing a black hole, and on one of the day I also showed you the Intel True View technology, where I showed you that in one IPL we had cameras around the ground. So, each camera captures certain video, and you can choose the video to watch the perspective. Okay. So, besides video, there are also many other areas where we generate lots of data. Okay. So, this is a very old video, very old slide. At that time, they predicted that in 2025 we would need so much information. Okay. So, the information that we generate keep growing and growing, and the devices that store the information also should improve, so that we can store all the data. Okay. So, if you look at the contenters, I mean I already told you that 80% of the data in the data centers is stored in hard disk drive, around 20% of the data in Facebook or Google is stored in the solid state drive. So, hard disk drive is still the best in terms of the cost as well as efficiency, performance and so on. Okay. So, if data keeps growing and if hard disk drive technology cannot keep up with the growth in data, we need to look for contenders. Okay. So, if I look for various contenders, optical disc used to be one contender. So, DVD, Blu-ray, people said that this technology is better than hard disk drive, say around few years ago, but these technologies are gone now. Okay. No, almost nobody uses Blu-ray anymore, and these are some disk I used during my postdoc. This disk also gone, magneto-optical disk is gone. For a long time people were proposing some storage technology called holography technology. So, this also failed. Okay. So, this being 3D, so people thought that we can store more capacity in holography technology, but this also gone. The only successful technology so far is the semiconductor flash memory technology. So, the thumb drive or pen drive, whatever you use, they can store lots of data, but one problem is that the price of a solid state drive is like 5 to 10 times larger than the hard disk drive. So, what it means is that we need some new form of device to store lots of data. So, that is where this domain wall memory comes into picture. Okay. So, looking at the contenders and the way in which hard disk drive was growing, this scientist Stuart Parkin, he came up with this idea of domain wall memory or racetrack memory to store information. Okay. So, in this racetrack memory you have a racetrack in the 3 dimension. Okay. So, you are not only storing in the lateral dimension, but you are also storing information in the 3rd dimension. So, because of this, I mean you have 3rd dimension, right. So, as a result you can have very high capacity. Okay. So, the racetrack memory or domain wall memory was proposed as a high capacity memory to store large amount of information. Okay. So, in the racetrack memory you have a wire where you have lots of up and down domains, and you use, I mean you can call, say this is a bit 1, this is bit 0, something like that, and you can move the bits by sending a current through the domain wall device. I will explain how it works, and you can write information using magnetic field or the concept that we learned like STT or SOT, and you can use magnetic tunnel junction to read the bits. Okay. So, because of the 3-dimensional structure, this kind of device can store large information. Okay. So, that is the basically the concept proposed roughly 20 years ago. So, this is one example of how the domains will look like in a wire. Okay. So, this is the magnetic wire, then you can see that this is a perpendicular magnetic anisotropy material. So, when magnetization is black, you can imagine that the magnetization is going into the board, white means magnetization coming out, something like that. So, you can see that there is one domain, another domain. So, you can store lots of domain in a wire. So, this is a 2-dimensional wire where you have a lot of domains, but you can stack them. If you can stack them in 3 dimension, you have more capacity. So, that is basically the concept of domain wall device. Okay, so in the hard disk drive we learned that the hard disk is rotating, then we have an actuator that moves the read write head around. So, we can read the data from anywhere, but domain wall memory device there is no moving part. Okay. So, if you want to read the data or write the data, we basically have to shift the domain. So, we have to shift the domain from here. Let us say there is a reader here, and this is the reader that reads the information. So, if you want to read this particular bit, you have to move this domain there. Okay. So, shifting of domains is important when it comes to domain wall memory. Okay. So, I will show you the video first. So, here we have lots of up and down domains, and you send electrons through the domain wall device. So, these electrons help to move the domain from left to right. Okay. So, you shift the domain by sending a current through the domain wall wire. So, what happens here is shown in this picture. Okay, so, this concept, I mean you send a current through the ferromagnetic layer, then we learned some concept, right, spin transfer torque. So, here we are looking at the motion of domain walls because of spin transfer torque. Okay. Let us imagine that there is one up domain here, there is a down domain here, then this is the domain wall. Okay. Let us assume that there is a okay, let us assume that there is one spin up electron that is entering this side. Okay. So, this spin up electron is parallel to this. So, there will be no transfer of torque. So, we learned that if you have to transfer torque, the magnetization and the spin component have to be perpendicular, right. So, these two are perfectly parallel, there will be no torque on this particular spin, and when this electron comes here, there will be no transfer of torque. Again here there is no transfer of torque, but this spin and this particular spin, they are not parallel. Okay. There is some component of this particular magnetization or spin which is in the orthogonal direction. Okay. So, there will be a spin transfer, I mean spin torque transfer between this spin and this particular spin. Okay. So, because of that the angular momentum transfer will happen. So, this spin becomes up. So, you can notice that instead of at this angle, now this spin has received some angular momentum from this electron and it has gone up. Okay. But the electron will, I mean it is the angular momentum transfer, right. So, now the spin will become like this because they have exchanged angular momentum. Okay. Now, when this spin comes, so this spin will transfer angular momentum to this one, and you can see that this becomes up and so on. Okay. So, as the electron keeps moving, it will transfer angular momentum to all the spin. So, you will see that this domain wall has finally moved to this distance. So, initially the domain wall was here, but as more and more electrons come, there is a transfer of angular momentum between electron spin and the magnetization that you see here. As a result, the domain wall keeps moving. Okay. So, that is what causes the motion of the domain that you see in this picture. Okay. So, it is basically spin transfer torque is used to move the domain wall. Okay, so, this is how the shifting of domain walls work. So, when we want to read information, what we do? Let us say in this region we form kind of magnetic tunnel junction. So, this layer will be like the free layer. The layer on top is the reference layer, then we have a magnesium oxide, then you can imagine that this is like the free layer. Physically the free layer is fixed, okay, in position. Free layer does not move physically, but the domains below the magnesium oxide move. Okay. So, at some point of time, let us say here, let us say this, if the blue domain is completely here, then the blue domain means we have parallel magnetization state, it will give rise to low resistance. Let us say this pink layer goes directly below the magnesium oxide, then we will have anti-parallel magnetization. So, we will have high resistance. Okay. So, by depositing some magnesium oxide and a reference layer at one point of the domain wall device, we can move the domain walls and read ones and zeros. Okay. So, let us see how it works. Okay. So, we are sending current through the domain wall device, we are shifting the domain walls. So, domain wall gets shifted, now you will have low resistance, high resistance, low resistance, high resistance and so on. Okay. So, we can read ones and zeros by shifting the domain wall. So, for reading we need to shift, for writing also we need to shift. So, if you want to read information, you need to shift the domain walls. If you want to write information, also you need to shift the domain walls.
Sir, I have a question. These domains, they don't seem to be having particular size. I mean, size varies. Will that not affect?
I mean, this is an animation I asked someone to do. It may vary. It may vary. Yes.
Sir,
Yes.
this looks quite similar. It's use of lab thing or
Yeah, I mean, Skamion racetrack memory came much later. This is the first concept. So, this concept was proposed in 2003, somewhere there. Skamion appeared in the scene in 2012. Okay, so, they used this principle to propose Skamion based racetrack memory. Okay, so, if you want to write information, again we need to shift the domains and you can use a electromagnet. So, like we did in magnetic recording. So, you send a current through the coil, you will produce certain magnetic field. So, you can use this magnetic field to write information. Okay. So, this is one technique. So, the first proposal, as I said, it came very early, like in 2003. At that time we did not have this concept, I mean people were not discussing spin orbit torque. So, 2003 proposal came up with this electromagnets to write bits. Okay, so, here again you have to use apply current, produce a magnetic field, write information, and you have to continuously move the domains, so that you can write different domains. Okay, by applying certain magnetic field, you create a domain. So, you may also like create magnetic field in one direction or the other to create blue and pink domains. Okay, so, even for writing and reading, you need to keep moving the domains, and one other advantage that you see in the domain wall memory is that there are no moving parts. Okay. So, in hard disk drive you have a motor that rotates the hard disk drive, and you have actuator that moves the read write head, then you read or write data. So, if you look at the power spent by a hard disk drive, about 90%, 80 to 90% of the power is spent for rotating the disk and for moving the actuator. Because of the motors involved in hard disk drive, we spend a huge power there. Okay. Whereas, in the case of domain wall memory, we have no mechanical part, no motors. Okay, we are sending current through the wires to move the domains. Okay. There are no mechanical parts like in hard disk drive. So, this technology is also expected to consume less power than hard disk drives. Okay, let us do some questions. Okay, sorry, I need to reset. So, please join again. Okay, all of the above is the correct answer. So, we are using GMR, TMR to read information, right. So, magnetization of the reference layer is always fixed, but the domain wall magnetization can be antiparallel or parallel. So, we are using the magnetization direction to read information, and we are using the motion of domain walls to displace information. So, all of the above is the correct answer. Okay, next one. Okay, most of you are right. So, there is a grammatical mistake. So, it should be push the data. Okay, so, electrons spin, push the data. Okay, that is the correct answer. Next one. Okay, I never talked about inductive head. Okay. So, the correct answer is magnetic tunnel junction. Next one. Okay, most of you are right. So, power consumption of domain wall memory is expected to be lower than that of a hard disk drive. Okay, so now let us go into the details of a domain wall device. So, we learnt the concept of domain walls before. So, when we have a magnetic material, if a large number of spins are pointing in the same direction, magnetostatic energy is going to be large. So, in order to minimize the magnetostatic energy, magnetic materials may form domains. Okay. So, this is something that we learned before. Okay. So, if the magnetostatic energy, the minimized magnetostatic energy is much larger than the exchange energy and anisotropy energy, then the system will form domains. But if the exchange energy and anisotropy energy are larger than the minimized magnetostatic energy, then the system will not form domain, it will be in a single domain state. Okay. So, this is something that we have learnt. So, in magnetic recording media, in hard disk media, we have tiny grains separated by some grain boundary. Okay. So, there are grain boundary which separates the tiny grains, and in these tiny grains the exchange energy and anisotropy energy will get larger. So, this system will be in single domain state. Okay. So, here we use some special techniques to have different composition in the grain and the grain boundary. Because of that, we will get single domain state. But normally, if you deposit any ferromagnetic film without any special technique, you will have this kind of domains. Okay. So, this is something that we have learnt already. So, here the way the domains form depend on the material and the material properties. Okay. So, if you have a perpendicular magnetic material, you have formation of two walls, one is a Neal wall, another one is a block wall. So, in Neal wall, as I said, the magnetization go from up to down by kneeling down. Okay. So, this mnemonics you can use to remember. So, in the block wall, the magnetization will go into the board, then come out, finally it will come down like that. Okay. So, the domain wall width is determined by the exchange constant A and the anisotropy constant K u. So, why is it proportional to A? Why it is inversely proportional to K u? Anyone has any idea? Why the domain wall width is proportional to square root of A, the exchange constant? So, this exchange constant is same as the Heisenberg exchange integral that we learnt. Okay. We are using different units here. Heisenberg exchange integral is energy per area per centimeter square, something like that. Here we are talking about energy per length per centimeter. So, that is the difference between J and A, but you can assume that they are almost same except for what we divide by. Okay. So, why the domain wall width is proportional to square root of A and inversely proportional to K u? Okay. Exchange constant wants your neighboring spins to be parallel to each other, right? That is what we learned. Okay. So, if they are like this, then the energy is going to be very large. Okay. So, what exchange constant prefers is that this change happens slowly. Okay. So, the transition between one spin to the other spin, the theta is very close to 0, changes slowly, then the exchange energy will not be high. Okay. So, what exchange energy does is to make the transition very large. Okay. So, that is why the width is proportional to A. So, what does the Ku want? The Ku does not want any spins in the hard direction. Okay. So, let us say perpendicular direction is the easy direction. So, if Ku is high, if many spins are in direction like this, right, away from easy direction, then the anisotropy energy will be increased. Okay. So, Ku want all the domains to be either in one of the easy direction or the other direction, and it wants fewer spins to be away from the easy direction. Okay. So, that is why Ku tries to minimize the width. If Ku is large, the width will be small. So, this is the reason behind this whole concept. So, why we are talking about domain wall width here? Any idea why I am talking about domain wall width?
Resolution of each bit differential.
Resolution.
One domain to another domain if you want to separate.
No, we do not want to, we are not worried about separating domain. We are reading information of magnetization of one domain pointing up, another domain pointing down, right. We are not worried about the resolution, but what is the other reason? Huh? Speed, no. Storage density. Okay. So, imagine if your wall itself occupies 50 nanometer, if your domain wall itself occupies 50 nanometer, then you need some space to have spins pointing up, and you need some extra space for the next domain where the spins are pointing down. Okay, so, we do not want the wall to occupy large space, we want this wall to be like as thin as possible. Let us say if this is only 5 nanometer, then say you can use the next 20 nanometer or so for magnetization pointing up, next 20 nanometer for magnetization pointing down and things like that. Okay. So, we do not want very large domains. Ironically, if you look at the domain wall devices, right, most of the earlier studies were carried out on pomeli. So, if you look at 2003 to say 2010, for a long time people studied the domain wall of pomeli for domain wall memory, but in pomeli the domain wall width can be as large as some micrometer. Okay. Because people are only studying the concept, it does not matter. When you are studying concept, it is okay, but when you ultimately want to make devices that operate at high densities, we need to consider which material will give rise to narrow domain walls. So, that is where the domain wall width plays a role. It determines the density of information. Okay, so, here I show you the domain wall density of various materials. So, in principle, if you use high Ku materials, you can achieve narrow domain walls like 3.6, 4 nanometer kind of domain wall width. As I mentioned, if you use pomeli, this domain, these are all in nanometers. Okay, the unit is missing. But pomeli will be like several micrometer width. Yeah, so the domain wall widths are in nanometer for different materials in this table. And as I mentioned, a lot of people worked on pomeli, but that is okay for a starting investigation. Okay, so how do we write domains? So, my earlier study, I mean when I introduced domain wall, I told you that we can use an electromagnet to create a domain. but since the earlier proposal, people have studied various mechanisms of writing domains. So, one approach is to, let us say this is the ferromagnetic nanowire, and this nanowire is part of a larger pad. So, people nucleate some domain here. So, for example, if the ferromagnetic nanowire has magnetization pointing to the left, the nucleation pad has magnetization pointing to the right, and you can push this domain into the ferromagnetic material. Okay. So, that is one way. So, you push the blue domain into the ferromagnetic nanowire, that is one way of creating domain. Another domain is, another way to create domain is like the concept that we learnt in field switching MRAM. Let us say you send a current through a wire. So, you will produce a magnetic field based on the Biot-Savart law. Then you can use that magnetic field to create domains. Okay. The third concept to create domain is to use spin transfer torque. Let us say this is the wire in which you want to create domains. So, you can have a copper spacer layer here, then you have another fixed layer. So, you send the current through this. So, this will have the spin transfer torque mechanism. Because of that, you can create reverse domain. Okay. So, if you remember my talk yesterday, I talked about using this spin transfer torque to create domain here. So, this is another way to create domains. So, basically this is the writing process. Okay. So, writing alone is not enough, we need to move the domain walls. So, we can move domain walls using many different methods. So, one way to move domain wall is by applying external magnetic field. So, this is okay if you are doing research in lab. You want to see the domain walls move, you can use your electromagnet in the lab and move the domain walls. So, in this picture you can see the researchers applied external magnetic field and moved the domain wall from here to here, then 21 millitesla the domain wall moved here and so on. Okay. So, this is good enough for lab, but we cannot use this in a product. Okay. So, for product this is not useful. So, if you are making a product, you want to send a current to move the domain wall. So, this current can be spin transfer torque or spin orbit torque. Okay. So, in spin transfer torque you send current through the wire. Okay. So, this is one example of a spin transfer torque through the wire. So, in this case we have a wire, the domain wall is here, you can see the difference between white region and gray region. And when before we send any current, the domain wall was here. Okay. After we apply this current, you can see that the domain wall has moved from here until all the way here. Okay. If you apply slightly larger current, the domain wall gets displaced from here and has moved until here. Okay. So, this is an example of domain wall motion by spin transfer torque. So, in spin transfer torque, the current flows through the magnetic layer. So, if you remember a few slides ago, I told you that we have domains like this, and the electron spins interact with this spin particularly, then we have domains like this and so on. Okay. This mechanism I described, that is the mechanism of spin transfer torque. Okay. The current flows through the magnetic material and the spins interact with the spins of the magnetic material and move the domain wall, that is spin transfer torque mechanism. Okay, so you can understand the spin transfer mechanism by looking at the LLG terms. So, this is the Landau-Lifshitz-Gilbert term. Then current induced domain wall motion is in this term and here. Okay, you do not need to worry too much about this theory, but you can, if you want to simulate the domain wall motion, you can take an equation like this and you can simulate the motion of domain walls. I think we can skip these slides. Okay, the second method to move the domain wall, or third method to move the domain wall, is spin orbit torque. So, we learnt about spin orbit torque a few days ago. We take a heavy metal like tantalum, then we send electrons through tantalum, and because of the spin orbit interaction, one type of spin goes to the top surface, another type of spin goes to the bottom surface, and we use these spins to switch magnetization in the SOT MRAM memory. In the case of domain wall device, we use these spins to move the domain wall. Okay. So, that is spin orbit torque induced domain wall motion. Okay. So, we have learnt about how do we write information, how do we move information. Reading is based on TMR, magnetoresistance concept, which we have already learnt. Okay. But this domain wall device concept has many challenges. One challenge is how do you fabricate vertical wires. Have anyone done lithography in your research? Okay, making lithography just along the horizontal direction itself is challenging, but if you want to create wires in the vertical direction, it is easy to draw, but difficult to achieve practically. Okay. So, this has been a challenge for many years, people have not solved this problem. Okay. So, one solution I have is like you can have planes, for example, this is one plane, this is another plane, like you can have many different planes. Within these planes you can have horizontal wires. Okay. So, instead of projecting these domain wall devices vertically, let us say this is one plane where you have zigzag wires, this is another plane and so on. Okay. So, you stack many planes on top of another, then probably we can solve the 3-dimensional arrangement. Okay. So, if you stack many planes, n number of planes, let us say each of these stores information at certain density. Okay, so, here I have done some calculation. Let us assume that 15 nanometer pitch is possible. So, that means like 5 nanometer domain wall width. So, this area occupied, this length is 10 nanometer. So, when we say pitch, right, whether semiconductor or any other technology, when we say pitch, it is the center to center distance. So, if center to center is 15 nanometer, domain wall is 5 nanometer, basically 10 nanometer is used for storing the magnetization of the domain. So, if you are talking about a wire with a width of, again this pitch of 15 nanometer, then the aerial density is like 2.86 terabit per square inch, and if you stack many layers, if this n is 64 for example, then we can store 137 terabyte. Okay. So, this is a potential capacity of a domain wall device. On the other hand, if you want to achieve a similar capacity using hard disk drive, you need to stack 11 disks. Okay. I mean, if you use 11 disks, then this density is almost not practical now. You need more than 11 disks to store that high disk data. Okay. So, this is some possibility in which the array stack memory could be useful. Okay. The second challenge is pinning domain walls. Okay. So, if you look at this picture, we have a domain wall device. We apply some current to move the domain walls. You can notice that the domain walls moves quite randomly. Okay. So, when I showed you domain wall device, the domain, each domain was like this, right. But here you see the domains are quite random. So, how do we pin the domain walls? So, there are many different ways people have researched about pinning the domain walls. So, one of the earlier concepts, I mean this is what we want like one domain, other domain like perfectly arranged, but what we see is something like this, okay, some random regions getting reversed. Okay. So, one technique people have used often is the notches. So, notches are basically physical features. So, they cut away some material here and some material here. So, that is a notch. So, these notches can act as pinning sites. So, there are some research in this direction. Then, so my group has done a lot of work on how to pin domain walls. So, one another configuration is this kind of staggered nanowire. So, we have a step like structure. So, in these step like structures, all these points will pin the domain walls. Okay. So, in this image, these are the regions where we have this step like structure. So, you can see that the domain walls get pinned. Okay. So, there are various methods like that. Let us do some questions. Okay, all of the above is the correct answer. We can use notches or we can use staggered geometry. Okay, all of the above is the correct answer. Domain wall memory has a 3D geometry, so we can have high capacity and it does not need motor, so we can operate at low energies. Okay, so both are correct. Okay, so this one you already saw yesterday. So when you deposit a magnetic film, the magnetic film will have some different composition or different property at certain regions. So if you look at the energy landscape, that particular region may have a lower energy compared to the rest of the region. So when the domain wall moves, it will get stuck here. Okay. So these are the regions where a domain wall can get pinned. Okay. And this is what happens when you take any magnetic film, but you cannot rely on these random pinning sites. For devices, you want to make pinning sites in a controllable way. Okay. You want to define, this is the region I want to pin the domain wall. Okay. So, you can achieve either by creating energy barrier like this or energy wells like this. So, domain wall will stop here, and in this case the domain wall will roll down and it will stop here. Okay. So, by creating energy barrier or energy well, you can create pinning sites. So, again we have done lots of work, I am not going to discuss this today. So, these are examples of pinning sites, how the domain walls get stopped and so on. Okay, then the third point is domain wall velocity. This was a problem for some time in the early days. So, people realized that the domain walls may have different velocity depending on the magnetic field you apply and so on, but most of these problems got solved. Now, people can move the domain walls with very high velocity. So, for example, if you use synthetic antiferromagnetic structures and you use spin-orbit torque, you can move the domain walls at speeds of 750 meter per second and so on. There are some later studies which even report larger, much larger speeds. Okay. So, speed is not a problem. Then another important problem is resistance and Joule heating. So, you have a wire, you send the current through that wire, then you are going to produce Joule heating, which is proportional to the resistance of the wire and the square of the current. Okay. So, you will have this Joule heating. This is some real problem. Okay, so that is all about domain wall devices for storage. I already talked about neuromorphic computing yesterday. So, we will stop here. Any questions? Yes.
So, for moving the domain walls, we are using polarized current.
And
since these wires will be quite long, so that polarization won't be get lost.
Polarization won't be okay. So, as long as let us say we have certain domains, and let us assume that these domains do not collapse into each other. Okay. So, there is something that keeps them apart. Okay. So, they do not collapse into each other. So, if that is the case, if you are moving this domain, then everything should shift, right. So, it is like, I mean, I do not know what analogy I can give, because I have never thought about this one, but if these domains do not collapse into each other, if you push this one, everything should move. first domain, yes. Because this domain cannot collapse into the next, okay. There is something that prevents the collapsing of domain. So, once you move this domain, the other one will move. Again, I mean, maybe let's take a train compartment, okay. There is one door here, another door here. Let us say there are people lining up from all the way from this door to the other door, okay. So, if one person goes in, then this person has to come out, right. It is like this person pushing this person and so on. Finally, you cannot squeeze one person into another person, so they have to come out, something like that. I do not know if anyone can think of better analogy, tell me.
Then like this it feels like the first domain you want to move is like we have this torque, the concept. Others will move just by momentum. Like,
Yeah, we can say that. Yes. This domain cannot go into this domain, okay. And all these domains have something that restrict collapse of the domain. So, once you move this one, they should all move. Yes.
How this restrict domain memory is different from Skamion, because Skamions also we like
Skamion is a modified version of racetrack memory. So, in racetrack memory, you are using, let us say this is one domain, okay, it has certain magnetization. So, you are using this magnetization to read the signal. Okay, so, in Skamion based memory, within this region you have one Skamion and you are using this Skamion to read the data. Okay. So, is exact, I will not say copy, inspiration of the racetrack concept. Okay, this one I skipped, I think. Okay, maybe I spend 1 or 2 minutes. So, I told you that there is something that prevents the domains collapsing into each other. So, the thing that prevents the collapse of domain into each other is this property called the chiral domain wall property. Okay. So, this chiral domain wall can be achieved by some newer kind of interaction called DM interaction. Okay. DM interaction is from two scientists, Zalozhansky and Moria. These two scientists came up with the two theories one after another that explain what happens in certain material, where the neighboring spins can be like this. Okay. So, we know that Heisenberg interaction states that the neighboring spin has to be parallel to each other. But somewhere in 1950s, people noticed that in some materials the neighboring spins are at some angle, okay, not parallel. So, they try to understand what happens, what causes the neighboring spins to be tilted at some angle. Okay. So, for that these two scientists came up with an explanation. Okay. So, I will not go into the detail. According to the Jablonski-Moriah interaction, the energy will be given by let us say we take two spins I and j, then the energy is given by this expression d I j cross product S I cross product S j. Okay. That means, if you take two spins, the two spins will be orthogonal, and this d I j is also a vector that will be again orthogonal to the two spins. Okay. So, this d I j dictates that the neighboring spins can be, I mean, if this is the only interaction, the neighboring spins will be perpendicular to each other, that minimizes the energy of the system. Okay. But in real magnetic system, you may have this Jablonski-Moriah interaction plus the Heisenberg interaction is of course there. Okay. So, in real ferromagnetic systems, you will have a competition between d I j and the Heisenberg exchange interaction. Okay. So, when you have both of them present, so you have not only the Heisenberg interaction, but you also have the Jablonski-Moriah interaction. So, in that case, the neighboring spins will not be completely parallel, they also cannot be completely perpendicular. Okay, because of the competition between the two, you can have neighboring spins at certain angle. Okay. So, this gives rise to the minimum energy state. Okay. So, this is observed in some material systems, where you, for example, if you grow cobalt or something on top of platinum, okay, top cannot be platinum. So, only one side you can have platinum. Then there is a Jablonski-Moriah interaction introduced by this interface that can make the spins to have this kind of arrangement. Okay. So, this Jablonski-Moriah interaction is the cause of observation of skyrmion. So, if you have a magnetic film of cobalt deposited on platinum and certain condition, you will notice that in this film we can have skyrmions. Okay. Skyrmions are like spin textures. When we say spin texture, what we mean is that the spins are not parallel, but they are tilted with respect to each other. Okay. So, outside the skyrmion region, you will have all parallel spins like in a typical Heisenberg system, but there are some regions where these two will compete with each other and form skyrmions. Okay. So, this property is called chirality. So, when you have the Jablonski-Moriah interaction, you have chiral behavior. Chiral behavior is like people say, I mean, people use the hand to say chirality. So, if you have two hands, right, they have mirror symmetry, I can superimpose them, mirror symmetry, they match, but if I move, they do not match. Okay. So, this property is chiral. So, if some molecule or something, if you flip the two molecules and they match each other, but if you shift them, they do not match each other, those are called chiral molecules. So, in a similar behavior, we have chiral domain walls. Okay. So, in the case of chiral domain walls, you will have say one domain wall facing magnetization in this direction, another one domain wall is like this, another domain wall is like this, in between you have the domains. Okay, so, let us look at these two domain walls. So, these two domain walls are in opposite direction. So, if you do mirror image, they will match. Okay. Mirror image, they can be superimposed, but if you shift this to this side, you will see that one of them is like this, another is like this, they are different. Okay. So, this kind of domain wall is called chiral domain wall. So, if you look at the neighboring domain walls, they all will be like this, this and so on. So, there is a chiral domain wall formation. It happens because of the Jalovsky-Moria interaction. Okay, so, this chiral domain wall gives rise to the stability. So, you can imagine that this is like north pole, south pole, this is like south pole, north pole. Okay. So, all the neighboring domain walls will be again like north pole, south pole, things like that. Okay. So, you know that you cannot bring two magnets of north pole, south pole closer to each other. So, that is what keeps all these domains stable. So, because of this reason, you cannot collapse one domain into another domain, the domain walls are stable. Okay. So, that is why I said when you have many domains, they cannot push into each other. So, if you push one domain, then all the domains have to push. Okay. You have already learnt about neuromorphic computing. So, I do not want to go through them. So, that is the end of the domain wall devices. Thank you. So, we can go for lunch now.